Coming to us next is Mark MacAlester. He'll be talking to us about space weather effects on communications. Mark has more than 35 years experience with this, and believe it or not, actually a very important topic for those of us dealing with RF. So there he is. So we're running ahead of schedule again today, so that's good. I'd like to kind of keep that trend for a little while. After Mark is done here, we will take our 15-minute break, and would like to try and keep us ahead of schedule. For one, if we stay ahead of schedule through the end of the day, we get out a little earlier. But two, if we have somebody up here and we have a really good Q&A session, I want to grant the extra time for Q&A. So it's all yours. That is all up to you. It is your presentation, your stage.
Alrighty, sound check. So one of the things about my presentation is it's often been described as drinking through a fire hose. And by the time we get to the end of the presentation, folks are often a little shell-shocked. So if you have questions, my preference is to ask the questions during the presentation while it's fresh in your head, because a lot of people will forget them when we get to the end. Alrighty. So first thing I'd like to talk about is the fact that I'm not a space weather scientist. I'm not a researcher. My background is telecommunications. 15 years ago, I was working for FEMA. And those of you who know about the Denver MERS detachment, I actually worked in the program office for them, buying their comms equipment, doing the satellite services contract for them. And my boss came to me and said, you know, I'd heard about this space weather thing, and I'd like to know if it'll impact our communications. So I started talking with the scientists at the Space Weather Prediction Center, NASA, a bunch of different parts of NASA, the Air Force, ARRL, Ares, and I discovered that what I was learning about space weather and impacts to comms applied to everybody, not just FEMA. So in the process of that, I kind of became an accidental subject matter expert, because this has nothing to do with my day job. So what we're going to talk about today is we're going to look at the operational impacts. I'm going to spend very little time talking about what space weather is, because that's not why we're here. It's like, what's going to do to my equipment? That's what we want to know. And at the end of this presentation, you'll have enough information that you can actually inform your PACE planning. I heard that Jeremy Johnson did a PACE presentation yesterday. So this is just understanding what this hazard is like and what it's going to do for our PACE plan. So real quick, our sun is a very violent place. And it does something really weird. It flips its magnetic pole every 11 years. So the North Pole becomes South Pole becomes the North Pole. And this is what gives us the 11-year solar cycle. While it's doing this, it's about a 3 to 5 year process. Its magnetic field lines become really twisted and tangled, really messed up. And where magnetic loops poke through the surface of the sun, it lowers the temperature, and then we see that from the Earth as sunspots. Now these magnetic loops, you can kind of think of them as a bare copper wire with a whole lot of current running through it. And these loops are constantly in motion. Sometimes they touch. And when they touch, you get the equivalent of the solar system's biggest short circuit. What this does is it produces a solar flare, and the solar flare gives off a whole lot of electromagnetic energy, which is tracked by the Space Weather Prediction Center on the radio blackout, or R scale. It throws out a whole bunch of high energy particles, which is tracked on the solar radiation storm, or S scale. And if it's powerful enough, it can actually blow off a piece of the sun. And this is what we call a coronal mass ejection. It's solar plasma. And if it strikes the Earth, then we call this a geomagnetic storm, and that's the G scale. So these are the NOAA space weather scales, and they were based on the Saffir-Simpson hurricane wind scale, which is why we see 5 levels. They were produced in 1999, though, so we've actually learned a whole lot about space weather, and technology has changed a whole lot since 1999. So these scales are out of date. There is a process right now, there's an effort right now to rewrite these scales and make them global. So that's going to be a good thing, but for now, this is what we have. And it's important to understand when you read these scales, one, they're not properly calibrated. So if you have a geomagnetic storm that's at the 4 level, on the scale, it's listed as severe. But let's think about this. If you have a Category 4 hurricane and that thing's going to make landfall, you know the damage is going to be severe wherever that hurricane makes landfall, properly calibrated. But we have had 8 G4 geomagnetic storms in this solar cycle, just in the last about 3 years. And the question I always ask folks is, did you even notice? Because unless you're doing HF, probably most of you haven't. You haven't noticed it. So the scales are not properly calibrated. The other thing about these is that the descriptions in the scales are listed as effects, but people often read them as operational impacts. They're not. These are the effects that space weather can have, but those effects can be mitigated in some cases, and in some cases you can completely ignore the effect, depending on what you're doing, what equipment you're using, how you're using it. And then finally, there's no upper end to these scales. You can have a weak G5 geomagnetic extreme storm, which is what we had last May, or you can have a really strong one. There is no upper limit. All right, so where are we today? Right now, we are in solar max. This is the maximum point, the most sunspots we are going to see in this solar cycle. Solar max, while it lasts for several months, the process of flipping the magnetic pole does take about 3 to 5 years on the sun. And during that time, you get a lot more sunspots. Now, space weather, extreme space weather can happen at any point in the solar cycle, but it's more likely at solar max simply because you have more opportunity. There's more sunspots, you have more opportunity for it to happen. So that's where we are, and we're probably going to see increased activity through the end of 26. So I took this, I took this from the internet on Monday, and I wanted to highlight that sunspot group 4079 is the kind of sunspot group that produces extreme weather. And this is what it looked like on Monday. Now that sunspot has since rotated further to the edge of the sun. It's not really going to be a threat. But if we wanted to look for what a threat looks like, this is what it looks like. This sunspot had every characteristic for producing an extreme event, except that it was not active. It was a very quiet sunspot. So good for us, but just wanted to show this is what bad could potentially look like on the sun. For those who work with operation centers, those that work with any kind of monitoring type stuff, I actually recommend looking at visible pictures of the sun on a regular basis, kind of get used to what normal looks like. It's just like looking, at a weather radar, and you can tell the difference between, a line of thunderstorms coming versus just light rain. If you get used to looking at the sun, you can tell when you have to pay attention to something, and that's what I do. I look at this, and I'm looking to just see, do I need to pay attention to SWPC's forecast? Because if there's just little tiny sunspots, I don't pay attention to the forecast because it's not going to affect anything I do operationally. But when I saw this, I paid attention and I started reading their forecast real close. So what do we look for when we look for something that could be a threat to the Earth? So first, there's a particular launch window, as you can call it. If a sunspot throws off a coronal mass ejection, and in that particular launch window, which you can see in the box there, something that comes off of that is very likely to be Earth-directed. Size matters. The bigger the sunspot group, the bigger the flare that it can produce. Things like magnetic complexity, which we're not going to get into here, matters. The more complex the group, the more likely it is to produce something that's going to be of concern. and activity level. So we saw this, sunspot rotate onto the sun just, this week, and it wasn't active. So when they're not active, it generally means that there's less of a threat. Last year, the sunspot group that gave us the extreme storm, very active. We ended up having 8 major flares, 8 coronal mass ejections, and we got hit by 2 of them. The other thing is, this is more for people that care about space. Solar radiation storms, anything that is to the west, east and west are actually reversed on these pictures of the sun. Anything that's on the west side is more likely to produce something, solar radiation storm that we care about that can impact satellites in Earth orbit, impact polar communications. If it's on the other side, less likely. And for solar flare radio blackout events, especially if you operate HF, these can occur from anywhere on the visible disk of the sun. So one of the things in my presentations that I do is I focus on extreme weather. Because unless you operate HF, most of us are not going to notice space weather until it gets to extreme levels. Extreme happens. We had one last May. Last May was what we would call like a 1 in 50-year storm. It was actually very weak. The largest storm that we know about occurred September 1st and 2nd, 1859, and has since been known as the Carrington event. This event impacted telegraph systems, which was the internet of the day in 1859, impacted those systems globally. Everybody around the globe experienced impacts. If this event happened today, it could have some significant impacts to our technology. So we're going to go into the details of that. In May of 1921, there was another storm. This one was roughly half the strength of Carrington. This is considered the 1 in 100-year benchmark storm. This storm actually started fires in Manhattan on the electric grid that they had back in 1921. It also started fires in telegraph offices, burned out the transatlantic cable that existed at the time. So impactful, but not, about half of what Carrington was. More recently, in 1989, we had another 1 in 50-year event. This one was a little stronger than what we experienced last May. Collapsed the Canadian Hydro-Quebec power grid in just 92 seconds after storm onset, knocked out power for, I always get these numbers backwards, 9 million people for 6 hours. If you talk to the electric utilities and you talk to NERC, the North American Electric Reliability Corporation, which manages the power grid, they will tell you this is the thing they expect from space weather. They don't expect massive damage to our electric grid, the end of civilization. You might read some of that crap in the open media. But they do say that there is a possibility in an extreme event that we could see large-scale blackouts that could extend for hours to a few days. So when we talk extreme events, remember, we've got 3 different kinds of space weather that we're really paying attention to. So you get that solar flare. Again, that's the radio blackout scale, or R scale on the NOAA scales. Because it's moving at the speed of light, we get no operational warning. At the time you see the flare, energy's already here. These things are a day side only impact for, it's primarily again for HF communications, and in an extreme event they'll last roughly about 3-ish hours. Solar radiation storms, that's the high energy particles. Those particles start to arrive at the Earth in about 20 minutes, but it takes a couple hours for them to build up to the whatever level they're going to build to, potentially up to an extreme event. Last time we had an extreme solar radiation storm was 1972. These events can last for 1 to 2 days and a little longer in the Arctic. We'll talk about the specifics. And then finally, if we're talking geomagnetic storms, the smaller storms can take 2 to 3 days to go from the sun to the Earth. but the extreme storms are really fast. An extreme storm can get to the Earth in as little as 15 hours. The Carrington event took 17 hours and 40 minutes to get from the sun to the Earth. We know that because there was an astronomer in England named Richard Carrington who happened to be observing the sun when this flare happened. Problem that we have from an operational perspective is that these coronal mass ejections, they're plasma. They have a magnetic field. That magnetic field has an orientation, and if it's, say, it's the same orientation as the Earth's magnetic field. Remember when we were kids, you put your magnets together, you put a North Pole and a North Pole together, they repel. Well, oddly enough, it actually works the same way with a coronal mass ejection in the Earth's magnetic field. If they're in the same orientation, they will essentially repel and the coronal mass ejection will bounce off. I mean, it's a lot more complicated than that, but that's essentially what happens. This actually happened in 2003 during the Halloween storms. During those storms, there was an almost Carrington level event, but when it struck the Earth, it was the same polarity as our magnetic field. It didn't, we didn't all learn about space weather in 2003 because of that. Last year, when we got the extreme event, it was opposite the Earth's magnetic field. So when you put a north and a south pole together, they connect, they click. That's the way it happens with the coronal mass ejection. That's why we had the impacts we did last year. But we won't know what that orientation is until that coronal mass ejection reaches 3 spacecraft that are about 1 million miles closer to the sun than the Earth. Those spacecraft will measure that magnetic field and tell us. But in an extreme event, that means that that coronal mass ejection is only about 15 minutes away from striking the Earth. So, I always talk to, the people that do, public affairs, public messaging. It's like everybody in the world is going to know this thing's coming. But you're not going to know if it's going to be a bad day until about 15 minutes before it hits. So that's a very challenging environment. This is just a fun slide. You can actually tell visually if you can see the aurora. If you see green, it's weak. It's a weak geomagnetic storm. If you see yellows and purples, it's about a medium geomagnetic storm. If you see red, it's a strong geomagnetic storm. And the Carrington event was described as a red aurora with white spears. In the United States, NOAA's Space Weather Prediction Center is the official forecast, alert, and warning center for the United States government, just the same as the National Hurricane Center or the Storm Prediction Center. They have a great website. You can get all the latest information on what's going on space weather. You can subscribe to products that will, alert you when something's going on. I generally recommend that if you're in comms, you're in an operations center, subscribe to the stuff that's at the 3 level and above, 3, 4, and 5. 3 is kind of just good to know. 4, especially if you're doing HF, is something you need to pay attention to. 5 is absolutely something you need to pay attention to. Okay, first let's talk what space weather is not before we start getting into what it does to comms. A lot of people use space weather and nuclear EMP as if they're the same thing. They'll call space weather natural EMP. And this is actually very confusing because a nuclear detonation has 2 pulses we care about. One is called the E1 pulse. That pulse is a high energy, high frequency pulse that can directly damage electronics. And then there's an E3 pulse, which is a low frequency pulse that can damage, essentially what is a large antenna like the power grid. Space weather has no E1 pulse, which means it is not going to directly damage electronics here on the Earth. Different story in space, but here on the Earth, it does not directly damage electronics. So the question I get asked is, do you need to disconnect your antenna if there's space weather coming? And the answer is no. Now, if you knew a nuclear detonation was coming, the answer is yes. You disconnect your antenna from your radios, you take off the power cables for your car battery, and that's how you protect your equipment from that EMP pulse. But for space weather, no, you can leave your stuff connected. The only thing I do recommend is if you have critical equipment, put it on an uninterruptible power supply that can handle both over voltage and under voltage conditions. The reason for that is if you get a geomagnetic storm that actually does some significant impact to the power grid, you can get voltage fluctuations on the grid, so anything plugged into that is going to be susceptible to whatever's going on there. So uninterruptible power supply for critical equipment is a good idea. It's a good idea anytime, anyway. All right, so we're going to talk radio, we're going to talk satellites, and we're going to talk terrestrial communications, wireline. We'll start with radio. Biggest takeaway from this slide, if those of us who do comms, we know this stuff. Space weather affects the ionosphere. So most of the effects that we are going to see that impact communications is going to impact stuff that either has to refract off of the ionosphere, like HF, or goes through the ionosphere, like satellite comms. If you're underneath the ionosphere, for the most part, you're not going to be impacted. So we'll start with what NOAA calls a radio blackout event. This is from that solar flare. This is the electromagnetic energy. Now, the one thing that I'm working with NOAA to change is the name of this, because radio blackout event is not a radio blackout event. You see the top bar, that's the radio spectrum. You see the bottom bar, you see the part in red, that's the part that's impacted by space weather, and it's skywave comms. If you're doing HF ground wave, if you're doing any other kind of stuff, not going to be impacted. Which means that when we're talking land mobile radio and cellular and line of sight microwave, these systems, even in the most extreme space weather events, will not be directly impacted. Now, I say directly because they rely on power, and we're going to talk power later on. So, as with any rule, there's always an exception. And the exception for space weather is something called a solar radio burst. When a solar radio burst happens, and this comes off sunspots, it may come with a flare, it may not come with a flare. These things are actually signals from the sun at radio and microwave frequencies, and can act as a form of natural jamming. But because of the distance, because of the atmosphere and everything, you have to really see this signal in order for it to raise the noise floor high enough that it's going to impact your comms. So where this can happen is, if you have a sun-facing antenna, directional antenna, that is, in cellular and public safety radio, we point those antennas down toward the horizon so we can increase coverage areas. Well, if this directional antenna happens to be looking at the sun while one of these solar radio bursts goes on, you can actually raise the noise floor high enough that you're going to interfere with your communications. This can happen at VHF and UHF frequencies to happen to line of sight. This can also occur when you have an omnidirectional antenna and some other antenna where they're transmitting and receiving antenna are on a direct line to the sun when this solar radio burst happens. This can actually cause enough interference to interfere with communications, but the good news is everything's moving. Because everything's moving, keeping that line of sight doesn't last very long. So this actually happened. On December 14th, 2023, there was the largest solar radio burst that's ever been recorded. It actually came from an unremarkable sunspot group. It occurred, so December 14th, it's winter. It occurred late in the afternoon. What this meant was the sun was low on the horizon. And it just happened to be at the perfect angle that you created that line of sight between aircraft in the air and air traffic control. From Seattle, Washington to Jacksonville, Florida, there were reports of aircraft operating on VHF and UHF losing comms with the towers on those channels. Fortunately, there's backup systems, so no aircraft actually lost communications. But on the normal VHF and UHF channels that they would be operating on, the static was so bad that for about 8 minutes at any one given location, they couldn't talk. Now, space weather is not the first thing people think of. When this happened, FAA first thought this was a system problem. And they started investigating, and they said, okay, it's not a system problem. You know, it's not some malfunction that they've got to deal with. And then they thought it was a cyber attack because of the national footprint of this particular effect. They came within 1 minute of declaring ATC 0, which means all aircraft get grounded across the nation. And then the Air Force called and said, hey, solar radio burst. So they didn't end up grounding the aircraft. And again, because everything's in motion, the line of sight didn't last for longer than about 8 minutes at any one location. So what this can mean for directional antennas in a cellular system or in a public safety radio system, if you have a sun-facing antenna, you know, so we're talking, you know, directional system pointed down to the horizon, we're talking dawn or dusk. If you get something that you know, comes and interferes with that direct, you know, the sun-facing antenna, the effect depends on where your radio is getting its coverage. If there's another antenna that it can connect to that's not a sun-facing antenna, you might maintain comms. But if you're only in the footprint of a sun-facing antenna when this happens, you might lose comms. But this is an effect that's only going to last for up to about 20 minutes. You know, if it's dawn, the sun is coming up on the horizon, eventually you're going to lose the line of sight. If it's dusk, eventually it's going to sink below the horizon. So the maximum effect is roughly about max of 20 minutes. And when I presented this to the cellular carriers, they said, yeah, 20 minutes. You know, we don't like that, but it's not a big deal to us. Okay, so let's move on to HF communications. This is what HF communications looks like. Again, this group probably knows this very well. During the day, you've got 4 regions in the ionosphere, DE, F1, and F2. You can do everything from near vertical incidents, skywave, out to long skip. This is what we do for HF. At night, the ionosphere changes. D region goes away. E region is a little iffy. We'll talk about that. And the F region combines into a single region. So, solar flare radio blackout. Remember, this is the electromagnetic energy. What happens here is you get X-rays off the sun. The X-rays interact with the D region of the ionosphere, increase ionization, which increases attenuation of signals, absorption of signals. And this starts at lower frequencies and moves to higher frequencies with the strength of the storm. So an extreme event is going to go to much higher frequencies and will last up to about 3 hours, whereas smaller events last less and generally impact lower frequencies. So at night, not an issue. There's no D region at night. So this is not going to affect HF comms at night. One thing that we found from the Hurricane WatchNet back in 2017, there was a R4 that occurred during the response to Hurricane Irma. The Hurricane WatchNet at the time used analog HF. Their HF was blacked out for 3 hours, exactly what space weather scales predict. But after that, it turned out that there was a UV, an ultraviolet light component to the flare that increased ionization in the F region. And the net control guy, Bobby Graves, told me that for the next 2 to 3 days, they had the best propagation he'd ever seen. So sometimes you get some good stuff coming out of this. Now, solar radiation storms and geomagnetic storms have different effects. Solar radiation storm primarily is going to increase attenuation in the D and E regions, and it's more of a polar effect. So this is a full coverage effect. It's often called a polar cap absorption effect. that goes from the pole to as far equatorward as the effect is going. Stronger storms, it gets closer to the equator. It is not highly correlated to the visible aurora, and for the most part here in Colorado, we wouldn't care about this. It's mostly an Arctic thing. If you're in Alaska, you're in Canada, this is the kind of thing you care about. But during an extreme event, this can actually move far enough equatorward that we can have CONUS impacts the same way they would in the Arctic. So this is something, these are generally longer lasting, 1 to 2 days, longer in the Arctic, so it's something to be concerned about. Now, geomagnetic storms are different again. Geomagnetic storms increase ionization in the E region and give us what's known as auroral E. Auroral E, highly correlated to the visible aurora, increases attenuation up to about 20 megahertz. The problem is a geomagnetic storm also depletes the ionization in the F region, which reduces your maximum usable frequency. So the combination of increased absorption in the E region and depletion in the F region means that you may not have any comms at all. We actually saw this last May. There's another type of space weather that people often don't talk about, solar minimum, when there are no sunspots on the sun. In order to be able to do HF skywave, you need some ionization in the ionosphere. If you don't have it, you can't refract your signals back down to the ground. In showing my age, in 2020, during the solar minimum, there was a 3-week period where there were no sunspots on the sun, and HF operators globally could not communicate beyond about 300 miles. So it's the kind of effect we don't normally talk about. It's not in the scales, but it does happen. All right, mitigation. First of all, digital equipment is far more resilient to space weather than analog equipment. If you read the NOAA space weather scales, they're based on analog voice. Digital equipment, far more resilient. In that same R4 that I talked about in 2017 during Hurricane Irma, FEMA had our units down in the Virgin Islands and Puerto Rico. We were using HF, digital HF. We never lost comms, even though the Hurricane WatchNet was completely blacked out on their analog at the time. They have digital now. So digital, better than analog, and if you're in tough conditions, data better than voice. Digital voice can go before digital data. I had a gentleman called Tom Whiteside. Some of you may know him. He wins a bunch of HF radio awards. He told me that during the Hurricane Maria in Puerto Rico response in 2017, there was an R3, and he couldn't do digital voice, but he'll still send email. He could do digital data, never lost connectivity with Puerto Rico. Another thing is remember that with a lot of these effects, the effect starts at lower frequencies, moves to higher frequencies with the strength of the storm, which means that if Hurricane WatchNet 2017, they were using 7 and 14 megahertz. FEMA, we could go up to 28 megahertz. Hurricane WatchNet couldn't talk, we could. So if you have the ability on your license to move to a higher frequency, you'll be more resilient. Also using higher power, and again, this is a license issue. If you can go to higher power, you can sometimes burn through the effect. We also noticed something, and this came from the military operating in Alaska, is that near vertical incidence skywave, for whatever reason, is more resilient to space weather effects. So if you only need to go short range, that using near vertical incidence skywave can actually make your ability to do HF comms, more likely. Going back to a geomagnetic storm, though, remember when the geomagnetic storm is going on, you get F region depletion. That means that frequencies that would normally refract off of the F region are going to go straight through into space. So the mitigation for that would normally be use a lower frequency. But if you're dealing with a geomagnetic storm and you have E-region absorption going on, you may not be able to get to a lower frequency to do that. Other mitigation techniques, station relay. You know, if the transmitting and receiving stations can't talk to each other directly, but you can both talk to someone else, station relay is a good way to work that. Also internet connected. So if you're familiar with WindLink, these are internet gateways. You can send HF email to this gateway. It'll go out to a HF transmitter that is outside of the effect of the space weather and hopefully get to your destination. So some of you may be familiar with shares. This is actually a network, HF network, that CISA runs the programmatics for over 3,000 stations across the United States, plus WindLink. So this is actually a very robust way to stay in comms. All right, let's talk satellite comms. For satellite, there's 3 orbits we really care about: low Earth orbit, medium Earth orbit, and geostationary orbit. There is another one, high Earth orbit. Most of us are never going to use that. Geostationary orbit is where we used to be. A lot of our ComSats were up there. If you've ever used a BGAN or an MSAT terminal, all that's from geostationary. That's where we used to be. Now, as we've all seen recently, there's a land rush to low Earth orbit. Starlink's got SpaceX's Starlink's got the initial foothold there, but there are a lot more constellations going up. Reason you go to LEO is because you reduce latency. You know, I've operated SATCOM for many years, and trying to go out to a geostationary and doing TCP/IP was a nightmare because you had 600 millisecond latency out to geostationary orbit. Low Earth orbit, Starlink measures it at about 20 to 21 milliseconds latency. Now, just put that in perspective, my cable network from Comcast Xfinity has 42 milliseconds latency. So Starlink is actually doing better on that one. There are some comms in middle Earth orbit. It's going to get more crowded up there. But right now, O3b is, which mainly supports like cruise lines and stuff, they're up there. Not something most emergency managers use, but Viasat is talking about putting a constellation in MEO. So this is what communications looks like at low Earth orbit right now. As you can see, there are a lot of providers out there, and they're putting up a lot of satellites, and they plan to put up a lot more. I actually read a Chinese article that talked about the carrying capacity of low Earth orbit, and they said that you could probably put about 50 to 100,000 satellites in low Earth orbit. Right now, between all the plans for satellites up there, far exceeds 100,000 satellites. So this is going to be something that, from a comms perspective, we're going to need to watch. Another thing that we look at from a trend perspective. So here's the satellite frequencies. Goes all the way from VHF to V-band and above. The trend here is to higher frequencies, and from a space weather perspective, this is a good thing. In order to do broadband from space, to get those high data rates, you have to use higher frequencies. Well, it turns out higher frequencies are more resilient to space weather, so that's a good thing. One of the problems, though, that we run into is that VHF and UHF are often still used for telemetry for satellites. So you could lose the telemetry on a satellite during a space weather event, even if the satellite itself can still maintain comms. All right, so we're going to talk about effects individually. So, electromagnetic interference. This comes from solar flare radio blackouts and solar radio bursts. Remember, these things can put out energy at the same radio and microwave frequencies that satellites operate on. So this is a form of natural jamming if you get that line of sight between the Earth receiver, the satellite, and the sun. Good news is everything's in motion, so this is a seconds up to about 15-minute effect. But But if you suddenly lose comms and there's space weather going on, that may be the reason. It may not be a cyber thing. It may not be something wrong with your equipment. So, solar radiation storms. Solar radiation storms are the real bane of satellites. These things can actually cause memory and command lines to suffer what's called bit flips. In the industry, they call these single event upsets. So if you flip even one bit, you can change the command that you just gave that satellite. You can change what's in memory. During an extreme storm, you could get 50,000 times the normal background for single event upsets. Now, a lot of modern satellites are designed to deal with this, but what it can cause is a very challenging environment for the ground operators of those satellites. The other thing solar radiation storms can do is damage solar panels. Not an issue for most satellites. They build in a lot of redundancy in those solar panels, but if you got an extreme event, NASA has predicted that you could lose 30% of the life of a solar panel, which means if you have a satellite that's operating close to end of life, that satellite could then not have enough power to operate. So when you're contracting your satellites, pay attention to age. Geomagnetic storms, different effect. Geomagnetic storms cause charging, both on the surface of satellites and that can cause charging inside the electronics. And we all know charging and the arcing that can come from that is bad for electronics. So there have been instances where satellites have been lost. It's rare, and a lot of the satellite vendors don't want to admit that's what happened, but space weather coinciding with sudden loss of a satellite, it's not necessarily causation, but it's really suspicious. And then geomagnetic storms also cause the aurora will heat the atmosphere, and the atmosphere will expand and increase drag for low Earth orbit. We saw this in May of last year. Not going to go into the mitigations for these. That's mostly for satellite operators. So you may have known back in 2022, there was a fairly minor G2 geomagnetic storm. SpaceX had just launched 49 Starlink satellites, and they launched them into the storm. Normally, what SpaceX does with their Starlinks is they put them in a low Earth orbit, and they test them to make sure they work before boosting them up to their operational orbit. That way, if it doesn't work, they can just deorbit the satellite. But the satellites were in that orbit when this geomagnetic storm happened, and you may have seen the video of Starlink satellites burning up. So, atmosphere expanded, increased drag, most of the satellites, 39 of the satellites were lost. Starlink has learned its lesson. SpaceX. They now test their satellites at a higher orbit, and they pay very close attention to space weather forecasting now. So this was learned from the school of hard knocks kind of thing. They also have their test orbit now at higher altitudes. So geomagnetic storms, remember we talked about auroral E. These storms actually create plasmas in the E region of the ionosphere. These plasmas are often called electrojets. These electrojets, because it's high current, we're talking millions of amps running through these electrojets, these plasma structures, you're getting current and you're getting magnetic field. And that wreaks havoc with satellite communications. Various types of communications impacts are put on the slide there. I did send these to Pam, so the slides are available for anyone who wants them. This is what causes what we collectively know as scintillation. Scintillation, though, is a highly localized event. You could have a satellite terminal at one location, completely scintillated. That same terminal on the same service 100 miles away, no scintillation. So one of the things I always recommend, if there's a geomagnetic storm going on and you have a satellite device that is being impacted by it, just keep trying. because that effect is not going to last forever. When we talk scintillation, remember I talked about how higher frequencies are actually more resilient. Scintillation starts at lower frequencies and moves to higher frequencies with the intensity of the storm. Even in an extreme event, what you see depicted there on the frequency scale thing is an extreme event. This is what it looks like. This is according to NASA's JPL. In an extreme event, by the time you get to the S band, that scintillation effect starts to fade out. By the time you get to the C band, scintillation should be gone. Which means, if you're using Starlink, or any of the other new LEO constellations that are going up, most of those are operating on KU, KA, Starlink is operating on V-band, and there's even talk about using higher bands beyond that. These frequencies are not affected by scintillation. So let's talk instruments. Iridium is an L-band system. MSAT G2s with Legato, very popular among wildland firefighters, L-band. Inmarsat B-band, L-band. These are the systems that in an extreme event could experience scintillation. What else is in L-band? GPS. So we could end up having problems with location on GPS, timing less so. So when we talk GNSS, Global Navigation Satellite Systems scintillation, and what it looks like from an end user perspective. One of the good things is, and I actually just discovered this not too long ago, this iPhone and my personal Android device, these modern phones have chipsets in them that can get both GPS and Europe's Galileo system. So these things can track up to 12 satellites. When you have scintillation going on, scintillation is not a whole sky effect. At a minimum, you need to be able to see 4 satellites to be able to get reasonably accurate location and timing. So the fact that these can see 2 different constellations is actually built-in resilience, and I didn't even know that until a few weeks ago. All right, so these same electrojets, I'm going to take a little detour and talk electric power, because electric power is a critical dependency for communications. The same electrojet that interferes with our comms, that plasma structure, millions of amps in motion, which means it produces a magnetic field. That magnetic field is large enough that it extends down into the earth. That magnetic field is in motion. A magnetic field in motion produces current. That current will run in the ground. So normally, we ground our equipment because we want to protect it from lightning strikes, short circuits. But in a space weather event, the current's in the ground. And it's looking for the path of least resistance to travel in. And sometimes it'll see those ground connections and it'll go up through the ground connections into the equipment. Now this signal is very, very low frequency, which means it needs a huge antenna to capture the signal. Just so happens our power grid is the perfect antenna to capture these geomagnetically induced currents. So what I just described is what this slide shows. And the problem is with these currents is that our electric system is designed for alternating current. That's what it expects to see. These currents from geomagnetic storms are so low frequency that it's called quasi-DC. When these DC currents get into our power grid, they cause a lot of problems. One thing that they can do is they can get into the big electric transformers, which are designed for AC. You put this DC current in there, it can heat the core of the transformer, and if it gets bad enough, it could actually destroy the transformer. And these large transformers are the ones that they have at power stations that actually take the power produced by the power station, put it up onto the bulk grid for transmission. There's about 2,000 of them in our country. If one of these gets destroyed, it takes 18 to 24 months to replace it because they're all custom built. The other thing that these DC currents do is they mess with the voltage on the grid, and they create what are known as harmonics. And these harmonics have the effect of tripping relays, causing damage in generators. So when these geomagnetic storms happen, this is the kind of thing, when people talk about the power going out during a solar storm, this is what they're talking about. These are the kinds of effects. Now, the good news is the electric utilities and the regulators have not been quiet. They haven't just let this exist. Back in 2013, new regulations came out requiring that the utilities do studies, prepare their systems for space weather events. That is actually why last year, all we did was enjoy the aurora. We didn't have to worry about power blackouts. The electric utilities had implemented all of the procedures they've been putting together for the last 10 years and kept the grid on. So when we talk power grid, this is very dependent on the geology, the local geology of a particular area. So the New England states, the Midwest, the area around the Great Lake in the northern Midwest, these are the areas that are the most susceptible to geomagnetically induced currents. You can see that in Colorado, less so. Now, if an extreme storm comes that affects the grid, NERC and the utilities say that the most likely effect is going to be what they call voltage instability leading to voltage collapse, which the rest of us call a blackout. The difference is this could be a regional or continental scale event. If there is no damage to the grid, the expectation is that power will be restored in most areas between 48 to 72 hours after the storm is over. Because obviously they're not going to do this while the storm is still going on. So that's a significant impact. If there is damage, then that damage could have more localized effects. A lot of it depends on how dependent a particular location is to electricity from the bulk grid versus from local power generation. Local power generation should still be good in most areas, but if there's damage, it'll affect the ability to move electricity around on the bulk grid. Problem is, we're not going to know which one it is right away. Department of Energy says that it'll take them about 24 hours to assess the grid and determine whether or not there's been physical damage on the grid. But I want to stress, NERC and the utilities do not think damage is going to happen. Now, these same electrojets can create geomagnetically induced currents in railroads, because they're long-distance conductors, and pipelines. The railroad industry says not an issue. The only thing that they say might be susceptible to geomagnetically induced currents is the railroad signaling. There's been no reported impacts here in the United States from geomagnetic storms. Pipelines, this is mostly for petroleum pipelines. What they do is, in order to reduce corrosion as they put petroleum through a pipeline, is they will actually run an electric current through the pipe. That is a way that they use to reduce corrosion, but if you get geomagnetically induced currents that are running through that same pipe, it can interfere with that signal and potentially lead to faster corrosion on a pipe. Not something that's going to cause a pipe to explode or leak or anything like that unless it's like really close to that anyway. But it can reduce the lifetime of a pipe. I don't talk about this, but it's fun if you get the slides. These are actual eyewitness telegraph operator reports from the Carrington event in 1859. And finally, we'll talk wireline. Now, in the United States, copper's going away. In order for GIC to go through a landline system, cable system, you have to have a conductor. Most of the stuff here in the United States, except for rural, there's still a lot of copper in rural. Most of it is now fiber. Fiber is not a conductor. Fiber is not going to be susceptible to geomagnetically induced currents. For copper, it's long-distance copper. We're talking tens of miles. So we're not talking local copper, from a central office in a large city to the local, local buildings and stuff. It's not going to be that. It's got to be tens of miles for you to be able to capture that signal and produce GIC. So still a potential issue for rural. And the only study we really have that shows one of these during the 1972 geomagnetic storm, there was a cable system in Illinois going to Iowa that did get knocked out. Cable was designed to handle a certain level of GIC. Turned out it was, the actual storm was higher than that. All it did, though, was trip the safety equipment. All they did is sent technicians in, reset the equipment, 24 hours, that cable was back in operations. The other thing that's raised a lot of concern recently is undersea cables. Undersea cables are responsible for about 95% of everything that happens on the internet. That's how we get, stuff from anywhere we want in the world. There was concern a few years back that undersea cables could be very susceptible to geomagnetically induced currents. But recent studies have shown that modern cables are actually pretty resilient. And even if they did get impacted, that impact would be, again, resetting safety equipment, putting the cable back into operation. And there's so many more undersea cables nowadays that if you lose one, there's often an alternate path somewhere. And the reason these cables are susceptible is because even though it's fiber, they have to repeat that light signal about every 100 miles or so. So if the cable's a long cable, they have to put these repeaters into the cable. These repeaters require power, which is provided on a copper line. But again, right now, we don't think this is going to be a major issue. All right. So we've talked about what can happen. Let's talk about what did happen. So we're going to talk about the geomagnetic storm that occurred May 10th and 11th last year. That storm has been called the Gannon storm. This is in honor of Dr. Jennifer Gannon, who was a space weather researcher who passed away actually just like 8 days before this storm happened. Oh, by the way, I took this photo in my backyard. This is the aurora. Remember when I talked about how you can tell how strong a storm is by the color of the aurora? I knew that because it was purple, this was not the kind of extreme event I needed to worry about. It wasn't red. All right, so what happened? We had a sunspot group, 3664, that very active group, very large group. This group was actually as large as the sunspot group that caused the Carrington event in 1859. Good thing it didn't do that to us. This thing put out 8 major solar flares, 8 coronal mass ejections, and it was the combination of 2 coronal mass ejections that gave us the extreme storm. But if you look at the extreme event values, you see that last year's storm was only about 20% the strength of Carrington. So it was a good test case, but it's not the worst that can happen. This is what the Space Weather Prediction Center's website looked like, the only time I've ever seen G5 on their webpage. And this is what happened to the Earth. You had 2 major coronal mass ejections. Neither one of them by itself would have produced an extreme event. The actual prediction was for a G4. It was not for a G5. But what happened is these two coronal mass ejections, the one behind was faster than the one in front. It caught up to it right before it hit the Earth. And that's why we ended up getting pushed into an extreme storm. And, as I said earlier, most people didn't think that this was very impactful. They got to see the aurora. That was cool. Their power didn't go out. Unless you were doing HF, you didn't lose comms. But what a lot of people don't understand is that there was a lot going on behind the scenes that made sure that us as end users were not impacted. So first, let's talk the effects on power grid. So this storm, the darker the color, the more geomagnetically induced current would have been going into the ground at that point. You can actually see we had some of this in Colorado. But this does track. Where do you see the biggest impacts? New England states, Mid-Atlantic, northern Midwest around the Great Lakes, especially on the west side of the Great Lakes. So this is the actual sensors from the electric utilities that were tracking geomagnetically induced current that they were monitoring. So, again, you can see that where we would normally expect to see GIC, we saw it. New England states, Mid-Atlantic, Midwest around the Great Lakes. But there was a surprise in this storm. Notice Washington State on the border of Idaho. That's not something that people predicted. This actually caused some issues in Washington State. So this is what it looks like when these GICs are going through. The GIC at the place where they had the highest measurement, 175 amps of quasi-DC current that wasn't supposed to be there. Down in New Zealand, they actually measured 200 amps. So this is not small current. And this is what it looks like from PJM, one of the interconnects. This is what they saw on their system. So remember how I said that the other issue that these events, these GICs can cause is something called harmonics, which messes with the voltage on the grid. So they actually measured a 10 kilovolt drop during this event. But as you can see on the slide, it doesn't become a problem until you get to 25 kilovolts. So, again, stressing, last May was a weak storm. Even though it was extreme, it was a weak extreme. There are bigger that can happen, so we could still see issues from a larger storm. So let's talk about what we saw on radio. Exactly as we expected, no cellular systems lost comms, no public radio systems, land mobile radio systems lost comms, everything worked. Remember, line of sight doesn't interact with the ionosphere, not impacted, even in an extreme event. So exactly what we saw is exactly what we expected. Different story in HF. HF was severely impacted. So this is kind of what it looked like. You can actually see the impacts on that, the bar chart on the side. Again, effects start at lower frequencies, move to higher frequencies with the strength of the storm. So, what did we have from actual reporting? So it just so happens that the Armed Forces was conducting its crossband test on the day of the storm. Normally, they get about 400, 450 stations, HF stations that check in to net control, which is at Fort Huachuca, Arizona. They saw only 15% of the normal check-ins that they would receive. One of the folks I work with at NORTHCOM, he does HF for NORTHCOM. He said that it was like transmitting into a sponge. Nothing was coming back out. Geomagnetic storm, increased attenuation in the E region, so you're having fade of signal there. Depletion in the F region. So if you're trying to use a higher frequency to get over the effect, might go through into space. So he said for about 10 hours, 11 hours, he had nothing. And we heard a lot of this from around the country. Further south you were, less impacted. So from FCC filings, we have a radio amateur operator operating 40 meter. You know, he was saying that this is a person that operates a net, about 120 members. And Saturday, May 11th, almost all the bands were completely dead. Another FCC filing, we see this person was operating on 3 different bands, 10, 14, and 21 megahertz. They also had no comms at times, and it took a bit for this to recover. It takes a bit for the F region to, you know, get its ionization back after it's been depleted. It also matters that during the G5 extreme storm, you had an R3, solar flare radio blackout, D region effect, and you had a solar radiation storm at the S2 level. So not an impact here in Colorado from the S2, but just because we have one type of space weather doesn't mean there isn't other types of space weather out there. So what do we see in satellite? So this is a graph showing the loss of altitude due to drag for one satellite that didn't have propulsion on it to keep it up. So there was a very severe impact, you know, very loss of altitude. Now, one of the problems we run in here is that you have a lot of satellites up there now in LEO. And these satellites are on known paths, and there's a lot of debris out there too. So you know the orbits of the debris, you know the orbit of your satellite, you can make sure that you're not suffering impacts from those two coming together. But when you get atmospheric drag, not only are you changing the position of the satellite, you're changing the orbit of the debris. So the more satellites we put up there, the bigger the issue this is going to become. So satellite maneuvering, what did we see? During the storm last year, over 5,000 LEO satellites performed maneuvers in order to maintain position during this storm. That's a lot of satellites moving around. Again, if the satellite operators don't know exactly where their satellite is, and you change the orbit of the debris that's up there, chance for what they call conjunctions, collisions, becomes much greater, and this risk is only going to increase as you put more satellites on orbit. So, SpaceX, in their FCC filing, said that they experienced 2 to 3 times more drag at their lower altitude. The 300-kilometer altitude is where they're putting their direct cell Starlink satellites. And they experienced 5 times the drag at 550-kilometer altitude, which is where the rest of their constellation sits. Now, Starlink satellites, especially the version 2s, do something really cool. They can sense their environment. They know what the drag situation is, and they can autonomously, totally on the satellite, reorient the satellite to reduce drag. So Starlink's version 2, the version 1's not so much, but the version 2s and all their newer satellites are actually very resilient to drag. Not trying to sell them, but you know, they learned their lesson when they lost their satellites earlier. The constellation responded in real time. They said that some customers reported, you know, very intermittent loss of signal. We're talking less than a minute. Some customers talked about the fact that they had slower speeds, but the service stayed on. No satellites were lost. Iridium, very popular with emergency managers. Iridium shouldn't have been impacted based on what we knew, because we used to think that you wouldn't get significant drag effects above about 400 kilometers altitude. Iridium sits at 790 kilometers altitude. But turned out they had significant drag issues. So they brought in extra engineers in order to be able to manage their network throughout the storm. Never lost service, didn't lose any satellites, but it was a bit more fun than they wanted for about 24 hours. But what this shows is the operators of these systems understand the threat. They've learned the threat. And they've designed their systems so that they can deal with the threat. It worked in a weak geomagnetic storm. We don't know if it's going to work as well if we get a Carrington-level event. So, scintillation. Let's talk scintillation. What did we actually see? For the most part, scintillation wasn't an issue. The scintillation from this storm, if it reached the L band, it was the very low part of the L band. But we did notice that there were impacts to global positioning system. For most of those impacts, it wasn't something a user would notice. I always got to caveat this. I couldn't find a source material for the location error for the average user of GPS, so I asked AI. And AI tells me that for the West Coast, they saw a 0.5 meter, half a meter positioning error. If you were in the northern part of the country, the extreme north, you would have seen about a 1 meter positioning error. But when we think about this, when you're using Waze or whatever you use on your phone, half a meter to 1 meter, it's really not a whole lot of positioning error. You're not going to miss your next turn. And the fact that we did not hear on social media or anywhere else any reports of people reporting major GPS positioning errors, I'm inclined to believe what AI says. This actually sounds right. But there's another form of GPS that's very popular with farmers. It's called precision GPS, and there's actually a picture of it on this slide of what this looks like. This is from John Deere. And what the farmers do is they use a ground station that knows exactly where it is, and then that ground station stays in contact with the tractors. Tractors are using GPS, and between the two of them, they can get centimeter position accuracy so that they will do, their planting, and that planting will be exactly where they want it to be. They no longer need to do those extra rows, to where the little guide thing would go. I'm not a farmer. Very accurate, increases yield, very popular. This is now used by about 70% of the farmers in the country. It just so happened the storm last year occurred during corn planting season. So they had enough position error that either the farmers couldn't plant, or some of them that tried were not able to plant, to the degree that they would expect. John Deere, I've actually got their statements here on this slide. They actually put statements out warning their customers that there's, GPS is affected by the space weather that's going on, and telling their customers to, you shouldn't expect great position accuracy from the equipment. There are estimates that this cost about $500 million by not being able to do the planting when they needed to do the planting. Again, I'm not a farmer, but I'm told that, it's very critical that you plant at just the right time. But when we got to the end of last year, profits from the corn crop were only down about 1%, and 1% isn't enough for us to say it was because of the geomagnetic storm. Wireline communications, no reported impacts. So, finish on this one. When I gave this presentation last year to the state of Illinois, their public affairs people asked me, okay, so when we get these space weather things happening, where do we go? What do we do? How do we get to the right message to give to the public? And the good news here is the Space Weather Prediction Center, just like the Storm Prediction Center, just like the National Hurricane Center, puts really good information on their website, and they were out there doing interviews. They actually held a media event when everybody could call in, ask questions. They are a fantastic source of the text that you would use for public messaging. And then think about, in a really extreme event, the biggest thing we really care about is loss of electric power. So the same messaging that you would use for an ice storm, for any other kind of storm, anything that would affect electric power for hours to a couple days, that messaging is the same messaging that you can use for one of these. So finally, I always say, you already have plans. You already have, hopefully, PACE plans. Add space weather. This is just another natural hazard. It's not something science fiction. Train personnel, test your stuff regularly. Make sure you got backup power just in case. And remember your people, so questions. And I always go to this slide because I'm not a scientist. A lot of really smart people helped me put this presentation together, so I always like to give them credit. So, questions? All right.
Okay, with that being said, we are going to take a break. I do want to throw a